The significance of forged parts in numerous technical areas is demonstrated by their wide range of applications. No vehicle is driven without the aid of forged parts. They're primarily utilized as components in the engine, transmission and suspension. Forged parts transmit forces and motion, are dynamically highly loaded and totally reliable. Approximately 75% of drop-forged parts produced in Germany are sold domestically, while the remaining 25% are exported throughout the world. The primary customers are the automobile industry and their system suppliers, as well as mechanical engineering sectors. The percentages refer to domestic supplies measured in tons. The durability and characteristics of suspension systems are tested on dynamic testing rigs. In commercial vehicles too, numerous forged parts operate at high stresses with high loads, as pictured in this front axle application. Numerous forgings are also used for heavy-duty diesel engines and gearboxes in commercial vehicles, or for trailer hitches. Forged parts are used in the most highly stressed places of wear for heavy construction vehicles and machines for structural engineering. For example, numerous components for Caterpillar suspension systems are forged, as are excavator teeth. Forged parts with absolute operating safety and reliability are needed in ship and stationary engines, such as crankshafts, connecting rods, camshafts, tilting levers, valves, and fuel injection nozzles. Large steam turbines in power stations are equipped with forged shafts and turbine blades made from high-temperature alloys. As shown here for a diesel train, railway car applications for forged parts include engine components and safety parts of the undercarriage such as wheels, axles and brake components. For aircraft construction, parts are forged from steel, aluminium or titanium and include jet engine parts of high dynamic and thermal load, such as shafts and high-precision turbine blades, as well as parts of the landing gear. Rolled semi-finished bars are used in the manufacture of steering knuckles for vehicles. The forging blanks required are cut by shears and are heated to forging temperature by an electronically controlled induction furnace, in the case of steel, to approximately 1250 degrees Celsius. Preforming is performed on a reducer rolling facility equipped with an automated manipulator. The material is fed through the roller sets in several passes. Then an upset forging process for the material starts with a preforming press, followed by a bending process. In the next process stage, the steering knuckle is pre-forged on a forging press. By now the shape of the component is nearly completed, and finally forged in the finisher die. The flash, which is technically necessary, is trimmed on another press in a subsequent operation. The finished steering knuckle and trimmed flash. The first impressions are then hot-sized for the subsequent machining process. Controlled cooling from the forging temperature ensures the required mechanical properties of the part. In a final quality test, safety parts, such as these steering knuckles for passenger cars, undergo eddy current testing, fluorescent crack detection, and measurement verification on a multi-feature measuring device. All inspection data are documented. The automobile steering knuckles are now ready for delivery. Peeled steel bars are the raw material for differential bevel gears for passenger cars. The precisely weighed sheared pieces, which have been induction heated in a protected atmosphere to 980 degrees Celsius, are placed into the die by robot. They're single-stroke flashless forged. An infrared measuring beam controls the ejection of the forged bevel gear. Then comes the controlled cooling process. The ready-to-fit gear toothing of the precision-forged differential bevel gears is shaped by a cold calibration process. In automatic multi-stage presses, round bars are heated to forging temperature and, after shearing, formed in several steps into accurately measured forged parts. The slow motion illustrates the manufacturing of an axle stem for passenger cars. Mechanically controlled tongs convey the parts from one station to the next. This axle stem is manufactured with minimal draft. In hammer forging, the heated bars are transported by a conveyor to the double-acting hammer, pre- and finish forged, and trimmed. In this case, 2 forgings are made from 1 bar. Afterwards, the workpiece is clipped. Still hot, the clamp for an auto trunk hinge is bent into the final undercut shape. After shot blasting, the clamp is calibrated, punched and gauged for measurement conformance. The linked production of passenger car crankshafts also starts with billets, induction heated to forging temperature. The corners are flattened and the surface is descaled. The pre- and finish forging of a 5-cylinder crankshaft is performed in plain dies. Afterwards, the workpiece is clipped, the flash goes to the scrap bin, while the crankshaft is transported to the next station. A twister, an operation in which 5 strokes of the shaft are properly aligned relative to one another by twisting. The final operation in the production of crankshafts is hot sizing. During this process, the crankshaft receives its required accuracy in form and dimension. The dimensions are automatically tested and documented in accordance with a sampling plan by a 3-coordinate measuring machine.